It's like Coulomb's
Let me begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for your creation, this class. Just pray you to guide our steps, help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so I think there's an idea that I haven't shared with you guys that'd be helpful for like the last problem. And so I'm going to do an example which is related in some sense, but not in a very direct way. Now, this idea has been with us actually already, but I might not have really, maybe I haven't emphasized it enough, I don't know. But the idea is superposition, and the basic idea is just this. If we have a situation where we've got some charge distribution and we've got another charge distribution, if we want to find the net electric field, we can add the electric fields from both of the distributions together to get the net electric field. So, for example, imagine you've got like a plane of charge, right, with charge density sigma, right? And then over that, perhaps you've got a insulating sphere, right, like this. So it's directly on the plane. So this is a charged, uniformly charged sphere, let's say with Q, charge Q and radius R, right? We've worked both of these problems separately before, right? Now I'm putting them together. I'm going to ask a question. If we look at the point that's half of the radius, like right here at this point, what's the electric field there? So I'm asking, what's the electric field? Find E. A distance R over 2, you know, from the plane along the diameter of the sphere. All right? And so I'm assuming that the sphere is sitting half above the plane, half below the plane, right? So I can do two things, right? I can figure out what's the electric field due to the plane of charge, right? And so we could go through all that again, but we look at a little Gaussian cylinder, right? And we derive what's the electric field, you know, due to sigma. It would be what? At this point, we worked it out. It's sigma over 2 epsilon naught, right? Because the electric field goes perpendicular to the plane up, perpendicular to the plane down, and we worked it out. It has a magnitude of sigma over 2 epsilon naught, right? So that's the electric field due to the sigma charge. But what about the electric field due to the uniformly charged sphere, right? So I'm assuming somehow that, I mean, okay, fine, this is kind of an idealization. Be like, well, but you're saying that the charged plane cuts through the sphere. I'm just saying, okay, fine, there's no charge on the sphere technically where it intersects the plane, but that's such a thin plane, it's essentially a uniformly charged sphere, all right? So that's an idealization. I hope you can forgive me for that. Anyway, so what's the charge? So then going back to that, the second electric field I want is like from the sphere, all right? What's the electric field from the sphere? This is a spherical charge. What's that? So this is directly upward, right? Agree? So if I draw the plane charge like dead on, the electric field from that just goes like this, right? And down here like that, right? If I draw the field lines. So it's kind of boring if I just drew it like that, sideways. What's the electric field due to the sphere, though? That's a more complicated question, right? But we can figure that out by Gauss's law. What we'll do is we'll imagine a Gaussian sphere that's just like this, right? And so we have that the flux through that sphere is equal to charge enclosed divided by epsilon naught, right? By the spherical symmetry, the electric field at the point in question is the same in magnitude as everywhere else. And also, the electric field is completely symmetric, right? That's not true for the whole electric field, right? If I also included in this the electric field from the plane charge, I wouldn't be able to make the symmetry argument. So I'm only talking in this current discussion about the charge on the sphere. I'm disregarding the charge on the plane for the moment. So I'm dividing it into two pieces. This problem is two pieces, the plane part and the sphere part. I solve them separately. I add the answers together because the electric field obeys this principle of superposition. So what's the charge enclosed then of the uniform sphere? Well, I can get that from, 4/3 pi little, my little r is what? R over 2, right? So r over 2 cubed divided by 4/3 pi big R cubed. See, that's the fraction of the volume that is cut out by that little sphere, right? So I take that fraction times q. That gives me the charge enclosed, yeah? And divided by epsilon naught. Now this is all equal to what? Well, 4 pi r over 2 quantity squared, right? Times the electric field due to the sphere, which I'm calling E sub s. Okay, so then what? Well, the 4/3 pi cancel, right? Can you guys help me with the algebra here?
And the r.
Okay. They do. Do they all cancel? Oh, you're right. There's an r cubed there. There's an r cubed there. This one survives, right? So let's see here. We've got like an eighth, right? An eighth q. Is that right? Divided by epsilon naught times 1 over, looks like 4 pi r squared over 4. If I've done my algebra right, which is debatable.
Wouldn't the fractions cancel out because you flip?
Uh-huh. Are you saying that this is wrong? I mean, I haven't simplified it yet, that's for sure. But so these cancel. This gives me an eighth upstairs. I'm solving for E sub s, so this stays right where it is. I divide by this thing to get to the other side.
Oh, okay.
It's all good. So this gives me E sub s is apparently q over, what we got? These 4's be canceling, so it looks like 8 pi epsilon naught r squared, I think. Do we agree, disagree? I got some thumbs up, all right. Now that's not the answer yet, right? What's the electric field at the point? So to complete this thought process, we go, okay, so the net electric field at P is equal to the electric field due to the sigma plus the electric field due to the sphere, which is apparently sigma over 2 epsilon naught plus q over 8 pi epsilon naught r squared, and there you go. That would be the electric field at that point. I don't think we've worked an example quite like this before, right? This is really merging two different concepts. Yeah? This is kind of the sort of, well, I don't know if this is exactly the sort of thinking. It's kind of sort of the sort of thinking for the last problem in the homework, in the sense that, like, well, let me show you how the last problem in the homework would be different if it was different. Okay, so what if instead of the problem I gave you this problem? Plane with charge density sigma, plane with charge density sigma, right? So if we use the principle of superposition on this, what we got? So this one, we've got electric field lines that go like this and like that, right? They go away from the plane, and what's their magnitude? Sigma over 2 epsilon naught, right? And the other one, what's the electric field lines go from the lower plane? Yeah, so I should say that like all of the blue lines, they've got magnitude sigma over 2 epsilon, right? But the ones emanating from the lower plane here, well, same song and dance, right? I mean, the electric field lines go away from the plane, so like that here, right? But down here, the story's different. But again, the magnitude is what? Sigma over 2 epsilon naught. So you could talk about this as E1, right? And you could talk about the other one as E2, right? Say sigma 2 equals to, so right now I'm solving sigma 2 equal to sigma and sigma 1 equal to what? Sigma, yeah. For the sake of making this problem easier than your homework. But if you listen to what I'm saying, you'll be able to solve your homework. Because what you can do is you can apply the principle of superposition, right? You can find the electric field due to the upper plane, and you can find the electric field due to the lower plane, and then you can add those fields to find the net field. All right? So for my example here, it's especially stupid because they've got the same magnitude, right? So you just look at it and go, oh, so I've got just double this. So like up here, the electric field, let me put the answer for my problem, not yours, on the board. So we got like up here in this region, we have an electric field of sigma over epsilon naught up, right? In here, we have what? Electric field equal to? Yeah, 0 in there, right? Because you got the same up and down. So it's just 0 here. And then down here, you've got, again, same magnitude added twice, but it's down. So I'm just writing the direction in words, all right? You can say it's so you can say I declare up as positive, so E is equal to minus sigma over epsilon naught. You can write it in words, or you can put a minus, but you know. It's the old issue of like one-dimensional stuff. We can use words to indicate direction, or we can use plus or minus if we've set a direction for the plus and the minus. But there are a couple different conventions at play here, admittedly. So, yeah. So why don't we just use a Gaussian sphere here? I mean, not sphere, but say Gaussian cylinder. We could do that here, right? Check it out. So if I was to take, let me just draw it over here to be less busy. So if this is my charge sigma, this is my other charge sigma. And if I take my handy dandy Gaussian sphere like this, right? And suppose I put this cap and that cap an equal distance above and below the planes, right? And then I can go, oh, okay, so this has area A, this has area A. I got my field lines by the symmetry of the problem. They got to be pointing like this, right? So the net flux is equal to 2EA, and that's equal to Q enclosed, right? What is Q enclosed over epsilon naught? Well, look at it. There's two charges that are enclosed in this problem, right? There's the charge of the upper plane, and there's the charge of the lower plane, right? Up here, you've got a, sigma 1a, which is just sigma a, and then down here too, yeah? So you got the charge here, and you got the charge there, right? So we get 2, the 2's be canceling, the a's cancel, and you get, lo and behold, E is sigma over epsilon naught, right? Which is exactly what we found over here by the principle of superposition, right? In the upper and the lower case. How about the middle? What if I drew a Gaussian cylinder between these planes? This one, again, we can say that the flux is equal to Q enclosed over epsilon naught. Like, when does Gauss's law not apply? It's a law, right? So, game over. The question, though, is can you actually calculate it? Here I can, because this cylinder, I'm putting symmetric between these two planes. There's a complete symmetry here. Whatever the electric field is on the top, it must be the electric field on the bottom. And it's also clear that there's no electric field through the side, because if there was, it would violate the fact that these planes are infinite. So by the infiniteness, the largeness, the largesse of the planes, there can't be a side field. There has to be only cap fields, and as such, the flux is 2E times the area of this thing. Right? Because there's also an up-down symmetry. So whatever flux is through the top, the same flux has to be through the bottom. And that's equal to Q enclosed. Wait a minute, there's no charge enclosed. So 0, therefore E equals to 0 in the middle. Why can't you do this for your homework problem? What? Please? Oh, do it? No, I'm not going to do it. I'm going to put your homework problem. I'm not going to do your homework problem. I'm going to do a different problem. Check it out, yo. So sigma 1 equal to 2 sigma. And down here, sigma 2 equal to 3 sigma. Infinite planes, there's your charge. Why can't I just use Gauss's law on this one? Just like I did in this, right? Take a big cylinder, put it symmetrically above and symmetrically below, and like so, right? I mean, the planes are still infinite, so it's still the case that the flux has to be directly only through the caps and not through the side, right? So it must still be the case that the flux here is what? So I got A down here, I got A down here, right? I can draw E here, right? I can draw E here. So it's still a 2EA, and that's equal to the charge enclosed divided by epsilon naught. But well, here there's the charge down here, and there's the charge up here, which would be what? Well, it would be 2 sigma A up there and 3 sigma A down there. Divided by epsilon naught, right? Yeah. Yeah. So, okay, so yeah, apparently electric field is just a what? It's 5 sigma over 2 epsilon naught, apparently, right? And by the same token, I can take my I can make a little Gaussian sphere in here, right? I can put it symmetrically between the planes, and I can say, oh, okay, again, the flux is just like I did before, right? 2EA, and that's equal to 0. So electric field equal to 0 in here, right? It's almost like it doesn't matter which charge is on the upper plane and which charge is on the lower plane. So anybody care to tell me why I'm wrong? Because I'm wrong. This is not the truth. Everything I just told you is a lie. It's important to understand how you can... I've showed you how to apply Gauss's law many times, right? I have spent considerably less mental energy showing you how not to apply it. But I'm trying to do that right now. How do you not apply Gauss's law? Yeah.
Because Gauss's law builds off of the fundamental principle that the E's going in both directions are the same, and because I don't know what it's called, the little circle with the but because those two aren't the same, the two E's going in both directions don't equal equilibrium.
Exactly. That's exactly it. There is I lied to you here. This E and that E need not be the same because there is no symmetry between the upper and the lower. This one's got 2, this one's got 3. I can't just draw this and suppose that the magnitude of the electric field up here is equal to the magnitude of the electric field down here. To quote my community college professor, this dog does not hunt. In contrast, over here, there was a symmetry. See, because I had this charge and they were the same, and so this electric field and that electric field were, you know, in agreement, and that's why I could make this calculation, and why this calculation agreed with the superposition principle of looking at the planes separately, finding the electric field for each one and adding them together, doing vector addition. Yeah? That symmetry is spoiled over here, so I cannot make this argument, right? This is E1, this is E2. All I can say is that E1 times A plus E2 times A is equal to, 5 sigma A over epsilon naught. That's true, but that doesn't tell me what E1 and E2 are, because they're different. And I don't know how to use Gauss's law directly on this problem to solve it. Because I would have to think, in order to be effective in my application of Gauss's law, I would have to think of some Gaussian surface that I could put here where the surface would be symmetric with respect to the distribution which is given. If I'm thinking about both distributions at once, I can't do it. Like I can't, if I put a Gaussian thing that's symmetric with respect to this one, like above and below, well then this thing's still down here messing it up, right? So the only way to deal with it is to like just think about this at one time, figure out the electric field from the upper one, think about this separately, find the electric field from that, and then add them together. That's the way you do a problem like this, which is the same way I did the first problem. Although the first problem might not feel at all like these two examples, but it's the same idea, the superposition idea. Which is the same idea that we were doing before Gauss's law, right? Because to find the net electric field from a distribution of charge, what did we do? We found the electric field from a little bit of charge, and then we add them all up with integration, right? It's that idea again. So there you go. That was my main point for today. You guys got questions? If you don't got questions, I'm just going to start working problems. Yep.
Will anything related to superposition be on that task?
Oh yeah, definitely.
Like all the questions?
Sure. Well, I mean, if there's just one problem, it's a superposition of one thing. So how could it not be? The only way I can not have superposition is to ask the empty question, which is easier to grade. It takes less ink, but no, we use superposition a lot. Like all those early problems where we had like 3 charges and you're asked to find the net electric field, what did you do? You took the electric field from charge 1, charge 2, charge 3, took the vector sum of those electric fields as given to you by Coulomb's law. You're using superposition here. So I'm just suggesting you can also use Gauss's law in tandem with superposition, in as much as you can like take your charge distribution and the point where you're trying to find the field, if you can find symmetric things that are symmetric with respect to that question, you can use Gauss's law to your advantage, because nobody actually wants to like calculate the integral to find the electric field here, which would be non-trivial calculus 3, right? So use it wisely, but yes. I mean, will you have to use Gauss's law in the test? Yes. I mean, this test is on Gauss's law and Coulomb's law, pretty much. So let's look at something a little bit more relaxing. Number 21 from page 738. It's a 1 blue dot question. This should not require a lot of mental energy on our part. Although I don't think I have a calculator, so it might be really hard for me. Here we go. So it says a proton is placed in a uniform electric field, and the electric field, we're given the magnitude, it's 2,950 newtons per coulomb. All right, and we're supposed to calculate the magnitude of the electric force felt by the proton. So you got this proton sitting here minding its own business, right? You've got this electric field that's filling the space, right? And what happens? What's the electric force put on the proton? How do we do that? Something get unplugged? Oh, I'll get it. Did I not plug in the mic? Oh, it's just a gravity. It happens. That's why I try to put it up here sometimes. Thank you. So, all right. If that's the electric field, and that's a proton, what's the charge on the proton?
Positive.
It's positive, right? What's the magnitude of the charge, right? 1.602 times 10 to the minus 19th coulombs. Very good. The .02 doesn't really matter. I just remember that for some reason that I don't even know why. So what's the force? Where is the force? In the time when I respected Star Wars, I would have made a Star Wars joke here, but oh well. That time is gone. Yeah.
That was pretty sick.
Yeah, I haven't watched it. I just watched a review of it. I'm like, oh, goodness gracious, this is awful. It's just awful. Anyway, we don't want to talk about that here. No, let's not talk about it. 19 Coulomb. My brother has said for a while that, you know, Star Wars is just a movie about space wizards for children. And so I think he has a point, but some people take it somewhat seriously. My apologies. My office is full of Star Wars Legos for the most part, but that's because I like the spaceships. Anyway, so there you go. This is charge times the electric field gives us the force, right? And whatever that works out to. All right. Tell me that again. 4 point what?
725.
Uh-huh.
Times 10.
Negative 16. And what are the units on this? Newtons. There you go. So that's a force, right? I know, the force is everywhere. There we go. To be clear, that joke is based on the original trilogy, and that is all. So I maybe allow it to extend to the prequels, but I can't go farther than that. So Mandalorian was kind of okay for a time, but anyway. So that's the force. Then what else are you supposed to find out? So there you go. That's the magnitude of the electric force felt by the proton. And now we're supposed to find the proton's acceleration. So F equals to ma, right? That's still with us. You guys remember that? Sometimes you guys ask me, does physics 1 matter? Yes. Like this. So the acceleration is equal to the force we just found divided by the mass of the proton, which, I mean, everybody knows, right? So you have 4.7259 times 10 to the minus 16th newtons divided by the mass of the proton. Now, what is the mass of the proton? So you look in the book, or if you don't have a book, you Google it. Google it. Google it. But in the book, on the back cover, it tells us that the mass of the proton is 1.672 times 10 to the minus 27 kilograms. 1.672 times 10 to the minus 27. It's got more than that, but I'm just keeping the first couple digits, okay? So there you go. You take the quotient of these two guys. And, whoa. Really? Dang. That's big.
2.3 times 10 to 11.
So guys, what I do with something like this is I just do the numbers, and that gives me like 2.83, something like that. And then I do the exponents separately. See, minus 16 plus 27 is what?
Negative 42.
11. Meters per second squared. That was kind of funny.
So doesn't it have mass?
Hmm?
Is that faster than the speed of light?
Is that faster than the speed of light?
Well, it's just an acceleration.
That is an acceleration. So there is no upper bound on accelerations, just velocity. If you believe in that sort of thing, relatively speaking. I mean, I usually do. But at least in as much as the current parameters of the universe that we live in. I do think things can be entirely different during the creation event. All right, so in the back of the book, which I would remind you this is an odd problem, so we can check the answer. 21.21, part A, it says 4.72 times 10 to the minus 16 newtons. We got it. Good, good, good. And then part B, it's got 2.83 times 10 to the 11th meters per second squared. All right, we got it. And what was the final question? Part C, it asks us, what is the proton's speed after 1.8 microseconds in the field? So C, find speed after a change in time of, I already forgot the number, 1.8 microseconds. That is a fancy way of saying 1.8 times what? Times 10 to the minus 6 seconds. Mu is micro. How do you find the speed? Well, we got acceleration, and we got time, so it starts at rest, right? So the velocity is simply the acceleration times the change in time in this situation, because it is a constant acceleration, so you multiply these two numbers, and what you got? .8 times 2.83-ish. Oops. So I got something kind of sort of like 5.1 times 10 to the what? So I got a minus 6 times a 10 to the 11th. 11 minus 6 is 5. So we got 5.1 times 10 to the 5th meters per second. No worries, well under the speed of light. We're okay, right? Because while the acceleration is ginormous, it's also the case that what? Well, the mass of the proton is, well, that doesn't help. The mass of the proton is tiny. That's what made it so. Well, the time is short, isn't it? I guess that's mostly it. It's just a short time. So now, yeah, and the book has 5.09. I truncated it. I was worried about the my calculator actually gave me 5.09, so I'll put it back there. There you go. So as a general point of order, on the test, I really just want 4 digits for answers. I don't really care too much about significant figures, but I do want like 4 numbers in your answer. Does that make sense? So as a general rule of thumb, like if you keep 5 numbers for calculations, then your 4 numbers that you keep for the answer should be fine. That way you won't like round off your error to a wrong. Listen, I don't typically take points off for round off errors. But anyway. So, in fact, it's possible to get exactly the right answer with the wrong steps and lose points. So just to be clear, like it's not just the answer that matters. You guys know this. You've had physics before, but any questions? Yeah.
What would be given to us, like the mass?
Oh yeah, I don't expect you to memorize the mass of a proton. Nah. I do expect you know like epsilon naught. That you're expected to know, or the K, or like K is 1/4 pi epsilon naught. I do expect you know Coulomb's field, Gauss's law, and generally speaking, the formulas at the end of the chapters are a pretty good guide. Although I would say I never did cover the torque of a torque on a dipole. I skipped that. So sorry guys. You want me to come back and cover it? You don't need it? If I don't cover it, it's not on the test. So should I cover it? Not, we shouldn't cover it then, okay. Yeah. Not like I'm saving you like a lot of difficulty or anything. It's not a terribly difficult topic. It's just I didn't cover it. Okay, so next up here, if I got time, maybe. 21, what was next on here? let's see, I said, I did numbers 13, 79, and 57 in the problem session, the first problem session. So I've got like a list of 10 problems. I'm trying to just kind of carve my way through it. Let's see here. We probably can do 23 in the time we have. Might be able to do more. 23 is boring. Let's see here. I mean, it's not that boring, but it's kind of the same as the one I just did. Let's see if we can. See, that's 2 dots. I may regret this. I'm gonna do 23. I'm gonna keep it. I'm gonna try to keep it. I'm trying not to stress too much in class today here. So 23. I will try to do as many of these problems as I can fit in to the problem session today. I don't think I'll get through all of them, but I'll try. So 23. Here we have a proton traveling horizontally to the right with a velocity which is given 4.5 times 10 to the 6th meters per second. All right. And we're supposed to find the magnitude and direction of the weakest electric field that can bring the proton uniformly to rest over a distance of 3.3 centimeters. So what we want to have, we got the proton booking it here at V naught, call it V naught, and then 3 centimeters, and here's your proton velocity final equal to 0, right? And of course, we're talking about a uniform electric field. What direction does the electric field have to be pointing if that happens? So we're talking about an electric field that's this way, right? So it's pushing the proton back this way, slowing it down, right? It says the weakest electric field. So the weakest electric field would be the one that's directly opposite, right? Like if you had an electric field which was at an angle, that would not bring it to a stop. It would move it, like turn its direction or something. But anyway, if we want it directly opposite the motion, we got 3 centimeters. So how do you figure out this problem? What do you guys think?
The change in velocity is equal to the negative electric field.
How about, I mean, this is the delta x, right? Kinematic equations from physics 1. At the moment, I don't care about the time, right? So how about this? I do Vf squared equals V naught squared plus, 2a. Well, it's going to be negative though, right? But I'll just say plus 2a delta x. But of course, the a is going to be negative, yeah? So apparently, the acceleration we want is what? It's minus V naught squared divided by delta x, right? That's the acceleration we're after. If that's the acceleration we're after, what electric field do we need? How is acceleration related to electric field? Remember, we've got what? We've got ma is equal to the charge on the proton times what? Times the electric field, right? Yep. Oh yes, thank you. Thank you. So we can also solve the acceleration is what? It is QE over m, right? So this gives me the electric field must be what? Minus m V naught squared divided by 2 delta x times q, right? And so you can put in the mass of the proton and the charge of the proton and work this out, right? So let's do that. What did we have? The mass of the proton was 1.672 times 10 to the minus 27 kilograms, I think. Now V naught, we got to square that. So we got a 4.5 times 10 to the 6th meters per second, square that thing. And then we're supposed to, don't forget your minus, I suppose. That just indicates that it's that way. And 2 delta x. What's delta x equal to here, guys? I heard a 3 and I heard a 3.0. I heard a 0.03. We are going to take the 0.03 because we want to put it into meters, right? Very good. Don't fall for the centimeter trap. And then Q. Well, Q is that monstrous 1.602. It's really not monstrous. It's actually pretty tiny, right? 1.602 times 10 to the minus 19 coulombs. And how does that all work out? And we can dispense with the negative if it just asks us for the magnitude. And I think it just asked us for the magnitude. Yeah, find the magnitude. Oh, magnitude and direction. So we already said the direction has to be to the left, right? What's the magnitude? Did you guys figure it out for me? Yeah? 0.783. And the units are kilogram meters squared per second squared divided by C, which is also known as a Newton per Coulomb. And there's a minus here, right? So the magnitude is about 0.783 newtons per Coulomb. Let's check ourselves. Uh-oh, moment of truth here, right, guys? What was this? 23, right? Uh-oh. Oopsie. It's 23, right? Well, it says 3.2 times 10 to the, I'm on chapter 21, right? Yeah. 3.2 times 10 to the 6th. So, let's try this again. 1.602.
Is it chapter 22?
No, this is a chapter 21 problem. So I'm going to double check that number there. 1.672 times 4.5, square that thing, divided by 2, divided by 0.03, times 1.602. I get 904. Well, I haven't done the I got 904, but times 10 to the what? 12 minus 27 plus 19. I get 4. Just a second here, let me check. I forgot the answer back here. It says 3.2 times 10 to the 6 newtons per coulomb to the left. I mean, this is 10 to the 6th, right? If I didn't miscalculate, I got 9.04 times 10 to the 6th newtons per coulomb. Maybe I made a calculator mistake. I don't think this is right.
I think it's 3.3 centimeters.
Oh, it's 3.3?
I think so. Why did that?
Oh, it does say 3.3. Okay. Does that change it a lot?
I just forgot the square.
The 4.5 squared, yeah. Anyway, calculator mistake aside, this is how you solve the first part of that problem. The second part of the problem is what? How much time does it take for the proton to stop after entering the field? How would you guys answer that? So its velocity is equal to a times t, right? Since it's, well, that's not quite true, right? We have Vf equals V naught plus AT, right? Where A is negative, if you like. It's constant acceleration. So you can use that to figure out how much time it takes, right? Because you know the initial velocity, you know the final velocity, and you can calculate the acceleration if you go back to here, right? Actually, if you read the whole problem, it makes sense to calculate the acceleration separately and then use that number to figure out the electric field, because then you can answer part A and part B with the same calculation. And then C, what's the minimum field, magnitude and direction that would be needed to stop an electron under the conditions of part A? What's the difference? If instead of a proton, it's an electron. Well, yeah, there's two things that change. The one is that the electron has a negative charge, so the electric field has to go to the right rather than to the left to slow it down, all right? And then the other thing, like you guys told me already, is the mass of the electron is different, like way smaller. So it probably takes a smaller electric field to accomplish the same. But that's it for today. So if you guys come back for the help session, great. If you don't, I'll try to post it for you guys to watch later if you want. And I'll collect your missions first thing in class, and we'll talk about the solution of the mission next time.